Hi, this is the video for the 4 stats formulas or 4 probability formulas that we're going to be discussing, and for Venn diagrams and tree diagrams. We will start out today by actually discussing Venn diagrams. A Venn diagram is a diagram made of 2 or more circles. It is used in probability to show relationships between events. A rectangle S, for example, doesn't have to be called S, but if it is called the S, it's because it's representing the sample space of all the possible outcomes. It sometimes is referred to as the universal set. It's the big group out of which everything else comes. That's the sample space. Circles A and B represent unique events or specific events within that sample space. If it is possible for A and B to happen at the same time, then their circles are going to intersect or overlap or even be one inside the other on the Venn diagram. Here are some examples of Venn diagrams, and in the directions here it says that we are going to shade the region of the picture corresponding to each listed event. So these are written with descriptions that are, stories, but just kind of generically. So if we had an event A, in this diagram, event A is this region. Notice that it includes part of circle B, but it is the entirety of circle A. Okay? In question 2, similarly, this would be the entirety of circle B. Part of circle B is inside of A, but part of it is not. This next symbol you saw in geometry class, and it means intersection. It's a very important idea. This idea of intersection is important to probability. We want to remember that, sorry, my handwriting is so horrible with this new stylus and laptop that I've been using. The idea of intersection is one of overlap. And we want to think of it along with the word and. So this means things that are in A and in B, which would be this region of the Venn diagram. The next symbol right here is the symbol for union. I guess I actually didn't write intersection on the last one, so I'm going to go back and do that real quick. I think the stylus sometimes thinks I want to move things and sometimes understands that I actually just want to write. So sorry about the little clunkiness here. Okay, so union we want to associate with the word or rather than and. And what it is we want everything, or we want all things. So if you think about how at a lot of weddings you'll hear the union of 2 families, or the union of this man and this woman, or something like that. Union means bringing 2 groups together, taking everything, whereas intersection is like the intersection of 2 roads. It's where the roads overlap each other or cross. So union means that you want everything that is in group A, or in group B, or in both of them. So you see how that ends up being everything? It's all of it. That's what union is. Okay, on the next set of diagrams, we see a definition that's pretty important. It's going to come back in different places throughout this unit, and that is the word complement. It says the complement of an event A refers to everything that is not in A. It's like the opposite of A. And so notation for that you might sometimes see is just with a little C up in the corner. So the probability of a complement is found by taking 100% minus the percentage probability of A. So if I know, for example, that there's a 30% chance of rain, I know there's a 70% chance of not raining, because raining and not raining are complementary events. Okay? So here they ask us to shade, in number 5, shade the complement of A. So that would be everything that is not in A, which would be all of that. Okay? Not in B would be all around here, and then all in here, not in B. And then number 7 says to do the complement of the intersection. Well, the intersection, as you recall, was this overlap part in here, and so we want to do the opposite of that. So that would be the part out here, and here, and then anything that was in the sample space that wasn't in A or B. So the complement of the intersection. And the complement of the union, well, the union is everything in both. So this would be the complement of the union. I'll do this part right here. Okay. So that hopefully helps you get an idea of what, how we might make use of Venn diagrams. We didn't really do those with probability though. So understand that that's coming up still. I'd like you to pause the video for a minute and try problems 9, 10, 11, and 12. And then number 13, I want you to just take a guess. I know it's some vocabulary that we haven't gone over, but I want you to just take a shot, okay? So pause the video and try the problems on this next slide. Okay, here are my Venn diagrams. In number 9, I showed A and B overlapping because if you think about rolling a die, there are there are two numbers in group A, 1 and 2, because that's the group of numbers that are less than 3 on a die. And in group B, event B has the outcomes 2, 4, and 6. And so because they both have 2, that means that 2 would be here in this overlap that I'm indicating on the screen right now. So we need to have those groups be overlapping. In in 10, I meant to say, in 10, B is a bigger group of which A is a part. In other words, A is a subset because 2 is one of the even numbers. In number 11, we have groups that are separate because 2 and a 3 have nothing to do with one another. And in 12, set A and set B are exactly the same because they both describe all of the outcomes 1 through 6. So the term that I told you that we haven't really talked about yet, but I think you can guess at, is the word or the term mutually exclusive. This is a vocab term that you should make sure to learn. Okay, put it on the vocabulary list if you keep one. And what it means is that there's no overlap. So Venn diagrams are really nice because they can show us visually what that means. And so the group with no overlap, whoops, that's not taking the thing I thought, but sorry about that, not very good at this. The mutually exclusive group is this one, right? Oh, it's moving stuff again. I'm sorry. You know I'm trying to draw an arrow to 11. Okay, so mutually exclusive is this group here in 11 that has no overlap. That's what mutually exclusive means. No overlap. I still think I want to move things. Okay, there we go. So no overlap. That's what mutually exclusive means. The next problem definitely shows us how we use the idea of a Venn diagram in combination with probability questions. So read the stem to yourself. And based on this stem, we understand how many students are in math, how many are in history, how many are in the overlap. And then there's this other number out here that we need to think about at some point. I don't really know if you know what that means. I hope you know what that 17 means, but let's find out. Okay? Question 13 says to find the probability that a student takes math. So I look up here at my Venn diagram, and my math group is this one over here. And so there certainly are 23 people who take only math of these two classes, but these 14 people take math as well as history, but that puts them in this group of math people. Okay, so I would add together 23 and 14 and get 37, and it's 37 out of 80 would be my probability that a randomly selected student is someone who takes math. History is this circle. So the probability that a student takes history is found by adding together 14 and 26. So 14 plus 26 is 40. And so we're going to have 40. Oh, hold on. Okay, so as I was saying, you'd add 14 and 26 and get 40. And so we're going to have 40 out of 80, or 1/2 of the students that take history, according to our Venn diagram. The next question asks the probability that a randomly selected student is someone who takes math and history. Well, and means that we're looking at the overlap here. So that would be 14 out of 80, which could reduce down to 7 out of 40. And then the last one is asking about or. So that means someone who takes math, or someone who takes history, or someone who takes both. These are the people out here who take only math. 14 people take both, and 26 people take history. So we could think of this as 23 plus 14 plus 26 out of 80, and that would give us the correct answer of 63 out of 80. But sometimes we don't have this diagram, so we can't really see these numbers so easily. We just know numbers like these two, or maybe this one. And so an alternate way of thinking of this question would be to say, let's take the people who are in the math group, and let's add them to the people who are in the history group. And then let's subtract off the people who do both, because those 14 people were included in both of these groups, and we only want to count them once. That would also equal the correct answer of 63 out of 80. Okay, so remember this idea of adding together both groups and subtracting off the overlap, because that's a key idea that's coming up in a formula. All right, what does the 17 represent in the picture up above? This 17, I hope you know, are the people who take no math and no history. So 17 people take no math and no history, okay? And then the next question we actually can't answer until we talk more about this word. Are the events taking math class and taking history class independent? The answer to this is no, but we need to discuss what this word even means before that makes sense. And so here we are looking at independent events. Two events are independent if the occurrence of one of the events gives us no information about whether or not the other event is to occur. That is, the events have nothing to do, no bearing one on the other. If two events are independent, then if you want to find the probability of both of them happening, you can just multiply the individual probabilities together. So for instance, if you had two people who each had their own pack of regular playing cards, and we wanted to define the events as the probability that each of them draws the ace of clubs. So A is the probability that the man draws the ace of clubs, B is the probability that the woman draws an ace of clubs. Certainly one of their decks doesn't have any bearing on the other deck. And so in order to find the probability that both of them draw the ace of clubs, we just multiply the probability for each of them together. And so there's a very tiny chance, of course, that this would actually happen, that they would draw the same exact card, the ace of clubs. Okay? Another definition that we need to discuss is the term that we mentioned earlier when we were looking at the Venn diagrams and it showed the circles being completely separate. That's what's called mutually exclusive. So two events are called mutually exclusive if it is impossible for them both to occur at the same time, or both to occur together. So that is going to, if that is the case, if two events are mutually exclusive, then their probability of both of them, probability of A and B, is going to be 0. So this is what the mathematical definition of mutually exclusive is. Notice that it said back here, independent, which sort of sounds like the definition of mutually exclusive, but I promise you it is not. Says that the probability of A and B is the probability of A times the probability of B. It does not say it equals 0, right? Here it says the probability of A and B equals 0. Back here it said the probability of A and B is the probability of A times the probability of B. Those are two different equations, so make sure you're paying attention. This one is the one that goes independent. This one is the one that goes mutually exclusive, and that's the one that shows no overlap. Like on the Venn diagram, doesn't show any overlap. Okay, so there are 4 formulas that we use a lot for probability. These 2 formulas both have the word and in them, so if you're trying to find the probability of something and something else happening, you're going to use one of these 2 formulas. This one is the one that we talked about just a moment ago as working with events that are independent. If 2 events are not independent, then they're called dependent. And then the second probability in the formula changes to the probability of B given A. This part here is what is referred to as a conditional probability, and we will talk more about that in days to come. But I know as a math student, I always hated not having a complete picture going in, and so I'm telling you now that there's going to be 4 formulas, and we're not going to use all of them today, but I just wanted to tell you that that's where we're headed. I didn't want to tell you two and then later on say, oh, guess what, there's two more. I thought that it would be better for you to see it all at the same time. Okay, so there's two formulas for and problems. And there's also two formulas for or problems. So both of these are when you want the probability of something or something else happening. This is what we use when the two events don't have any overlap. And this version, which is identical, all of these terms are the same, except there's this other part out here. This part is necessary, this subtracting the overlap is necessary when you have overlap between the events. And we saw that on one of the problems we talked about back here with the math and the history. Remember how we took the probability of math plus the probability of history and subtracted the probability that a student was taking both? That's the formula we were using, and see how it was an or question. So probability of math plus the probability of history minus the probability of the overlap. We were actually already using this formula from here. Okay? All right. The last thing that's in this lesson is tree diagrams. And I know when I looked at the Xerox copy for your packet, this didn't come across very well in the packet. I hope you can see it better here. Tree diagrams are useful for organizing and visualizing outcomes when you have a sequence of events. Like say you wanted to roll a die 3 times, or you wanted to pull a card out of a deck of cards a couple times and then flip a coin. Sometimes that's hard to conceptualize without having something to look at. And that's the advantage of the Venn diagram as well. Venn diagrams give us something to look at and help us to understand a situation. That's true of tree diagrams as well. What we do in a tree diagram is we write out the outcomes of an event. And so here, this dot doesn't represent anything. The branching from that dot represents rolling a die once. And you can see here all the different outcomes. 1, 2, 3, 4, 5, and 6 are the different outcomes for rolling that die. And then you also write a number on each of these lines that is the probability of that outcome. Okay, so I will show you what I mean by this in just a second. This I included just to explain that tree diagrams are going to really make use of multiplication. So when we have things that are independent, probability of A and probability of B is the question we want. I want to know the probability of something and something else happening. I end up multiplying, and that can be something I can do without a tree diagram. But especially in cases where I'm not really sure if my events are independent or not, a tree diagram really, really helps. And I can just multiply the probabilities on each branch out, and I know then the probability of each of the different possible outcomes. Okay? So this is a little question that will work well with a tree diagram. Okay? So the first sentence is actually an example of that conditional probability idea. If it rains on a given day, the probability that it rains the next day is 1/3. Okay, so suppose that's true. Okay, like maybe we know this for our town or something. So if it rains on a given day, that's a condition. If it rains, then the probability that it rains the next day is 1 out of 3. So a conditional probability is something that has an if to it. Okay, just a little side note. Not super important for what we're going to do after this, but just pointing out that it is an example of a conditional probability. Okay, conditional probability. Okay. It also goes on to say in this problem, if it does not rain on a given day, the probability that it rains the next day is 1 out of 6. Then it tells us the probability that it's going to rain tomorrow is 1 out of 5. We want to know the probability that it will rain the day after tomorrow. So we're not interested in today per se, but we're not interested in the first day, we're interested in 2 days out. Okay, and we're going to draw a tree diagram. So to do this, we are going to first have a pair of branches that represent tomorrow. And tomorrow, it's either going to rain or it's not going to rain. So I used R for rain and N for not raining. And in the problem, the sentence that I underlined in green said the probability of rain tomorrow is 1 out of 5. So on this branch to the left, I'm going to write the probability for rain, 1 out of 5. And if there's a 1/5 chance of rain, then there's a 4/5 probability that it's not going to rain. I use the idea of a complementary probability there. It's the opposite. Okay, so that picture that I have as of right now represents the first day, tomorrow. This set of branches, all of them, this entire tier of branches, represents the next day. So the day after tomorrow, it either will rain or not rain. It will rain or it will not rain. I had to write that twice because I'm not sure if it's going to rain and then rain, or rain and then not rain, or not rain, then rain, or not rain and not rain. But those are the 4 different outcomes. Those are the 4 different pathways that could happen. Now we have to refer back to the question, and it said, if it rains on a given day, the probability of rain the next day is 1 out of 3. That's the sentence in blue. So if it rains, rain the next day is 1/3. So here is where it rained. So rain the next day would be 1 out of 3, which means that not raining would be 2 out of 3. It also said if it doesn't rain on a given day, the probability that it rains the next day is 1 out of 6. So if it doesn't rain, then the probability that it does rain the next day is 1 out of 6, which means not raining would be 5 out of 6. So if I need to figure out the probability, let's see what it was. What is the probability that it will rain the day after tomorrow? Well, there's 2 different paths that end in rain the day after tomorrow. And this path is the first one we're going to think about. That path has a probability of 1/5 and then 1/3. So I'm going to use the space down here. So 1/5 and then 1/3. Notice that when I said and with my mouth, I wrote a multiplication sign. That's going to be true all the time in probability world. Okay? The other branch that ends with rain is this one. Okay? And if you take a look there, that's going to be 4/5 times 1/6. And I said I needed that to happen and then that to happen. Now I don't need this outcome and this outcome. I need this outcome or this outcome. So I'm going to join these with a plus. A little extra line in there. There, let me fix that up. Okay, a little plus. Okay? And then we just do that calculation. So that requires us to do a little work with our fractions. We can do that though. Okay? And we're going to get 1/15 plus 4 out of 30. We need to get a common denominator. And so that would be 2 out of 30 plus 4 out of 30, which is 6 out of 30. And that reduces to 1/5, or if I wanted a percent, is what weather is stated as a lot, I would write that as 20%. So there's a 20% chance of rain the day after tomorrow, according to our information. The very next page in your notes packet has a chart for the 4 probability formulas. You're welcome to fill that in now, but we probably will start class tomorrow filling that chart in and making sure we're good on all our formulas. Thank you so much for taking good notes. I'll see you in class. Bye.